So we're starting the emerging scholar talk for this morning. I'll first talk with Evgeniya Akhmedova, who will tell us about the tropical amplituhedron.
Yeah, hi everyone. Thank you very much for inviting me. I will be talking about the tropical amplituhedron. This is a work, a joint work with my advisor in Weizmann Institute, Ron Tesler. I'll try to stick to the schedule. Do my best. So a good thing about the conference, we can skip over the first few definitions. So I'll need to recall some definitions from tropical geometry, talk about the tropical positive Grassmannian, and then we'll get to the object itself and why we even want to think about it. So I'm skipping over the positive Grassmannian and the amplituhedron, and here I will just say which cases we will be focusing on. So the cases for m equal 1, k equal 1, where we have the cyclic polytope in the regular case, we would get a tropical cyclic polytope, and then some of the results are for the general NK and M, and what we were focusing mostly on was the m equal 2 case as just a simpler geometry than m equal 4 and more well studied, and I think a lot of people in this room have some results concerning it. For the m equal 4, it's the project we are currently working on. And we will be sticking to, when we have some pictures, we'll stick to a very simple example of m equal 2, n equal 4. And we will see it in the tropical case later on. So now let's recall a few definitions from the tropical geometry. There are two ways to think about it as of tropical varieties, as zeros of tropical polynomials or as valuations of varieties over the field of Puiseux series. There are more general definitions of tropicalization, but for now we will be focusing on these two. So the tropical semiring is the ring where we have addition replaced by minimum and multiplication replaced by addition. So we can see that quasi-addition in this ring is not invertible, which creates some problems for us. And the tropicalization of a polynomial is exactly replacing the products with multiple addition and addition with taking a minimum. And here we see that the tropical polynomial we get doesn't depend on the coefficients, real coefficients of the polynomial we started with, but the zeros of tropical polynomial are the points where this minimum is achieved at least twice. So this gives us a tropical hypersurface. And then if we want to tropicalize the whole variety, we need to take the intersection of all the tropical hypersurfaces given by polynomials in the ideal giving us that variety. It is also possible to define a positive part of a tropical hypersurface, but this definition is a bit more tricky. So we say that the point is in the positive part if the minimum is achieved both in a term that came with a positive coefficient and in a term that came with a negative coefficient. So here we see that it actually requires us to remember which polynomial exactly we tropicalized. And the positive part of the variety is the intersection of positive parts of the hypersurfaces cutting it out. So there is another way to think about tropical geometry as valuations in the field of generalized Puiseux series. This series has coefficients from real or complex numbers and real powers where the sequence converges to plus infinity. So we always have a minimal power in this polynomial series. And the valuation is a map that takes a series into the minimal power of a term in it. And for a series with real coefficients, this field is ordered, where we say that an element is positive if the coefficient of the term of this lowest degree is positive. So again, we have an ordered field, and we can define actually positive Grassmannian over it, and we can define Amplituhedron over it, because the only thing we need for positive Grassmannian is the order on the field. So now the tropical Grassmannian, we think about it more in the sense of tropicalizing the Plucker relations. But then again, by the fundamental theorem of tropical geometry, the tropicalization through tropicalizing relations would coincide with taking valuation of the variety cut out by the same ideal. So great thing about the tropical positive Grassmannian is that it is cut out by a relatively simple set of tropical polynomials, and this is a wonderful thing. We don't see it in the regular positive Grassmannian, and we also don't see it in the tropical Grassmannian itself, because those relations. Oh, sorry.
Maybe the attribution is incorrect for this.
Oh my God! Yeah, that's. Yeah, I'm so sorry. I completely forgot to fix it.
I mean, the first part is fine about the tropical Grassmannian. It's just the positive that you're missing. Anyway, don't worry. It's
okay. Yeah, sorry. Okay, so this is where a hope for a simpler object for the tropical Amplituhedron comes from. Part of it is that, yeah, we have the tropical positive Grassmannian having a somewhat nice structure. So what are our motivations to define the tropical Amplituhedron? Well, the tropical Grassmannian turns out to have connections to the triangulations of the Amplituhedron for m equal 2, and it's an interesting object in it of itself, the positive tropical Grassmannian. So generalizing this in the same way as the Amplituhedron generalizes the Grassmannian is an interesting thing to us. Then tropical geometry is a way to compute some asymptotics of functions, and then we could compute asymptotics of 3 amplitudes. Yeah, and possibly a simpler structure. So what we want to do is to make this diagram commute. We can take valuations from the Amplituhedron and from the non-negative Grassmannian, and yeah, we want to define the map from the tropical non-negative Grassmannian to what we want to be the tropical Amplituhedron, so that this map doesn't depend on the top row of this diagram. So we need a bit more requirements on the matrix Z than we had in the regular case. So normally you want the matrix Z to have all its maximal minors positive. But now we want the matrix Z to be tropically totally positive, which could mean that it is evaluation of a totally positive matrix where all minors are positive, or equivalently, which is a theorem, it is a matrix where all the minors have their minimal diagonal sum on the main diagonal, and there is a very simple criterion which would give us some of the combinatorial tools we use later on, that we only need to check this condition for the 2x2 minors of our tropically totally positive matrix. So we define the tropical amplituhedron as tropicalizing the polynomials, which give us the y coordinates in the regular amplituhedron, and just the fact that the diagram we saw before commutes comes from Z being totally positive. So what do we know about it? Oh, yeah, the map is well defined, and the dimension of the tropical amplituhedron is k times m. So it's the same dimension as the regular amplituhedron, and yeah, it's the same dimension as the tropical Grassmannian, which means that we're not doing something meaningless, and the tropicalization actually gives us an object that in some way reflects the object in the regular case. For k equal 1, we see that it is a tropical cyclic polytope, and we'll see an example of that in some pictures later on. The boundaries of the tropical amplituhedron are the tropicalization of the boundaries of the regular amplituhedron in the m equal 2 case. We don't know that yet for m equal 4. We had sign flip condition in the amplituhedron, and we get a tropical version of that. But in addition, we get something which, as far as we know, doesn't have a mirror in the regular case, but looks very much like the sign flip condition, the tropical sign flip condition. And then one of the main results is the stratification of the tropical amplituhedron by 2k dimensional positoroid cells, tropical positoroid cells. But here there is an addendum saying that we need to loosen some conditions which we had for the regular triangulation, specifically the injectivity condition. So here is an example of the tropical cyclic polytope on the right. And here we already see what the triangulation might look like. So yeah, the tropical moment curve is just the tropicalization of regular one. So sorry, I'll check the time. Okay. For the boundaries, well, I don't I don't want to bore you with the formulas, but the thing I want to draw your attention here to is that the boundaries have a very simple expression in terms of y coordinates, whereas in the regular case, we would have preferred the twistor coordinates. So here it's not that clear that the twistor coordinates are always the best thing, but we can go back and forth between them. So here is the definition at the top of the slide of the tropical twistor coordinates, just tropicalizing the polynomial given them. And below is a combinatorial tool which we use quite frequently. Oh my God, I'm sorry. In many proofs. Okay, here we go. Yeah, so when we have a tropical twister and we write it out in terms of elements of the matrix Z and the coordinates in the preimage, we know that the minimizing set, given the coordinate in the preimage, the minor, should not intersect the set of coefficients we picked for the twister. And here are the boundary twisters II plus 1 and twisters 1I that give us the sign flip condition. And we can see that they have to minimize in some very specific sets. So that are written in the lemma below. And we can see where the sign flip comes from. The sign flip is just the changing of this t by 1. So we had something minimizing in t plus 1. And then when we go to t plus 1, t plus 2, this is where the sign flip happens. And if we, here is, yeah, yeah, the regular sign flip is the minimizing of the coordinate 1i in 1t, then going to 1t plus 1. But now we can look at the minimizer above and see that it changes in quite a similar way. But here we don't have a sign flip in the regular case because all of our coordinates have to be positive. So this is something interesting we want to study more. Yeah, so here is the sign flip condition written out, and the min flip, as we call them, for the I plus 1. Yeah, I don't probably need to remind the positoroid specification thing, but what we had in the regular case, we required the collection of cells for the triangulation to map injectively, to map disjointly, and to cover all of the amplituhedron. But what happens in the tropical case? We have cells, we have positoroid cells, mapping not injectively, but separating into two parts. One part would map injectively, and the other part would map onto the boundary of the image. And again, when we see the separation requirement, we want only the interior parts to not intersect, because the boundaries would naturally intersect with each other. So here is an example of the triangulation in the simplest case. And here is the thing about the non-injectivity. So the tropical positive Grassmannian 1,3 is just the tropical projective plane. And we can take a chart x3 equals 0. And we have only this blue quadrangle mapping into the tropical amplituhedron injectively, but everything else collapses onto the boundary of the image. And on the right, written in black, you can see the specific conditions for this boundary. So where these and a few others like them are positive, the points where they are positive tropicalize into the blue part, and when they are negative, one of them is negative, it tropicalizes into the part, valuates into the part which collapses onto the boundary. So what we want to study here is separating the amplituhedron into the image of the part that evaluates into the white part and the part that evaluates into the blue part. And our hope is that this, well, we can see it as one part go into the limit, the tropical limit faster than the other. So we would have a leading part in this image of points tropicalizing to the blue parallelogram. Okay, sorry, I'll skip this. Yeah, and here is what we plan to do in the future. Describe this injective part of positroid cells in the general case, because what I've given, the relations I've given are just examples in the most simple case. We don't have the description in any generality now. Then we have started studying the M=4 case, and it gives some interesting results, for example, for the Formas box, where we have two solutions in the branching locus having different asymptotics, for example. And we also want to define the tropical loop amplituhedron and see if we can get some simpler structure in the tropical case. And then we can also think about the amplituhedron as a tropical, as a positive geometry, and try to define what the tropical positive geometry is. But this is more in the distant future. Okay, and that I think is all. And I think my time is also up.